hope you're doing well today. So we're going to talk about concavity in this section along with the second derivative test, which relates directly to concavity. Have a definition for you right off the bat. So if f is differentiable on an open interval I, in other words, you can take the derivative, concave upward, the definition now, concave upward means f prime of x is increasing. I think we really need to think about what in the world that is saying, okay? So first of all, I know you have a thought of what concave upward looks like, and it probably looks something like this, correct? That graph is concave upward. If you have ever had any physics, you talk about concavity, and you maybe talk about lenses or mirrors, and concave upward means this, where concave, oh look, I've got an error. Let me fix that, hold on. There we go, all fixed. So, concave downward, it did say upward a minute ago, means f prime of x is decreasing, okay? So, concave downward means this. Now, in physics, you might have heard of that's like convex because it's poking out and that's concave, but we're just going to say concave upward and concave downward. Now, how that relates to the derivative, let's talk about it, because let's think about this. The derivative on this side, okay? Now remember the derivative. This is a decreasing graph, right? But what is the derivative over here? Since it's a decreasing graph, the derivative is negative. Does that make sense to you? So again, from here to here, because that's decreasing, the graph is negative. Right here it's 0. So the graph of the derivative may look something like that, because it's negative. Okay, so I'm drawing it below the x-axis. Make sense? Sort of? Okay, now on the other side, what's the derivative doing over here? Well, it's positive, right? Because that's an increasing graph, therefore the derivative is positive. Again, right here it's 0. So it's going to be above the x-axis. Now remember what I just graphed right here, and if I made it one color, that's the derivative. So f prime of x. Now, the derivative, you see, is increasing. Kind of neat, huh? Okay, so if you have concave upward, that's what it's going to happen. The derivative is going to be an increasing function. Now, I'm not saying this looks exactly like this, but roughly it does. So again, the slope of the tangent line all the way to here is a negative value, so it's negative. Here the slope of the tangent line is consistently from 0 to a positive value, so I drew it positive. And that gives you an increasing function for the derivative. Now let's look at the other one, concave downward. Okay, so on this side, get my colors right, on this side, notice all of those derivatives are going to be positive, right? That's an increasing function. Therefore, all of my derivative on that side is positive. It's above the axis. So I could draw that like that. Now right here is 0, and that's that point right there. But over here, it's all positive. Now on the other side, my derivative, trying to find another color I haven't used. There we go. On this side, no matter what, the slope of the tangent line is negative. Here it's less negative than it is here, so that means it's closer to 0, so it's all going to be negative. Now let's think about what's going on. My derivative, when I look at just this line, is a decreasing function. And that's what this says, concave downward, which that's what you would imagine it would look like. The derivative is a decreasing function. It's fun to think about, isn't it? So we have a theorem here, Theorem 3.7. It's a test for concavity. So this is how you tell if a graph is concave upward or concave downward. Notice this is f is a function for which the second derivative exists on an interval I. So you must be able to take the second derivative. It says if f double primed, which means the second derivative, right, is greater than 0 for all x and I, then f is concave upward. So if your second derivative is positive, then it's concave upward. On the other hand, if your second derivative is less than 0, your second derivative is negative for every value in a particular interval, then your graph is concave downward. Notice it says straight lines are neither concave upward or concave downward. We'll talk about that third, but I want to address these two issues. Now again, by definition, this is the exact same picture, redrawn, of the definition of concavity. So remember, concave upward meant the first derivative, okay, was increasing. Now what this is telling us is we need to take the derivative of this. So the derivative of this guy right here, notice it's an increasing function. So the derivative of that would be positive. So no matter what, and I don't know where, you know, I'm not considering what the slope of this is, but it's definitely positive all the way through, which means we might have something that looks like that. Now we're not taking the derivative of that, that's just all positive. So that would be our second derivative, all positive numbers. Now on the other hand, for concave downward, and again this was drawn by definition, okay, and then this is the first derivative is a decreasing function, because again we were increasing our original function, made us positive, decreasing on our original function made this negative. Now if I took the derivative of the first derivative, that's all a negative slope. Remember, derivative is the slope of the tangent line, and since that's all negative, we might get a second derivative that looks like that. In other words, below the x-axis. Okay? So that's how this relates. Now, you're not going to have to draw pictures, but I want you to see how this really relates. But notice it says, again, if the first derivative is positive, we're concave upward. And if the second, I said that wrong. If the second derivative is positive, you're concave upward. If the second derivative is negative, you're concave downward. I do want to address the straight line issue. It says they're neither concave upward or concave downward. Now, well, duh, right? Because that just doesn't meet our idea of what concavity means. It's a straight line. But if you think about the definitions, if I take the second derivative of this, first of all, the first derivative of this I'm going to do in red. The first derivative of this is constant, right? So no matter what, the slope of the tangent line is consistent. So this might have a slope of 3. It's really not that steep, but let's just say it has a slope of 3, or I have a really big scale. So that means my derivative might look like that. So that's your first derivative, whereas the black line is your original function. Now what if I take the derivative of that? Well, you know, the derivative of a constant is just 0. Alright? And notice how it doesn't meet any of these. You would have the second derivative is equal to 0. So that's how that works. So it matches your intuition about concavity. A straight line is not concave, upward or downward, but it also matches the definitions we've been given and the theorem. So for our first problem, we're supposed to determine open intervals for which the graph is concave upward or downward. So we need a method, right? Well, we have a method. It's very similar to what we did in the last section when we were finding increasing and decreasing. So what we're going to do is we're going to do the second derivative in the same steps. So first of all, to get to the second derivative, we are required to take the first derivative. So here we go. For this polynomial, remember the domain for this polynomial is all real numbers. The first derivative is also going to be a polynomial. Use the power rule. We have negative 4x to the third. Derivative of 4x to the third here is going to be plus 12x squared. And then the derivative of 8x squared will be plus 16x. I just use the power rule, the sum difference rule, and the scalar multiple rule. Now I'm not going to use that, but if I did, that would find increasing, decreasing, relative maximums, and relative minimums. Okay? But we're going to move on to concavity, so I need to take the second derivative. So I'm going to take the derivative of the derivative using the power rule. So 3 times negative 4 is negative 12x squared. Don't forget to reduce that exponent by 1. Plus 12x squared, move the 2 in front, that's 24x to the first. And the derivative of 16x is 16. Now, remember, the rule says, if I go back and flip over there, it says if the second derivative is positive, it's concave upward. If the second derivative is negative, it's concave downward. So we need to find out, first of all, where it's equal to 0, just like when you find critical numbers. These are not officially called critical numbers, but what I like to do is call them critical numbers for the second derivative. Okay, but really it's just a method, so critical numbers really only apply to the first derivative, but it's the same idea, folks. So we have 0 equals negative 12x squared plus 24x plus 16. And now I've got to solve this equation, right? So if I factor out, what could I factor out? A 4, a negative 4. So negative 4, that's going to leave me with positive 3x squared and minus 6x minus 4. So I need to factor this polynomial, negative 4. That or use the quadratic formula. So if I try to factor it, I have to find numbers that multiply to be negative 12 and add to be negative 6. Don't think about that for too long. Unfortunately, I've thrown out a problem where we need to use the quadratic formula right off the bat. So this method, not going to work out for us. But now, all is not lost. The negative 4, we could divide both sides by negative 4 right here. And that negative 4 just simply disappears. So I'm really only focused on the 3x squared minus 6x minus 4. And to solve that, again, I need to use the quadratic formula. So I have x is equal to negative b. b is negative 6 plus or minus the square root of b squared minus 4. My a is 3 and my c is negative 4. And that's all over 2a. Remember, a is 3. So I continue. I'm going to come to the top of the page to simplify. So that gives me 6 plus or minus the square root of, that's 36, plus 4 times 3 is 12 times 4 is 48, all divided by 6. If I continue to simplify, that's 6 plus or minus the square root of 84 divided by 6, which is 6 plus or minus. And that reduces to 4 times 21. Square root of 4 is 2. Square root of 21 over 6. Finally, I can reduce that by splitting this up into two separate fractions. The 6 goes into 6 once, and the 2 and the 6 leave me with a square root of 21 over 3. Phew, right? But it happens. It happens, and I'm glad you got to see it in this video. So I have two critical numbers, so to speak, for the second derivative. One of them is x is equal to 1 minus the square root of 21 over 3, and the other one is x is equal to 1 plus the square root of 21 over 3. Now, I don't think it hurts to find out, like, actually how big that is if you type that in your calculator, because it's going to be hard to make a chart and figure out what's in the interval, because that's what we're going to do, y'all, is make a chart, just like we did in the last increasing and decreasing. So I need to know really how big this is. Now, if I type in 1 minus the square root of 21 over 3 in my calculator, I get about negative 0.528. And then I type in 1 plus the square root of 21 over 3, and I get 2.528. Okay? Again, that's rounded. Now, my next step is to create a table. So once again, now remember our domain goes from negative infinity to my first critical number for the second derivative. I'm just going to use a negative 0.528. Remember, that is rounded. And then we're going from negative 0.528 to 2.528. And then finally, for my last interval, we're going to go from 2.528 to infinity. Okay? Now this table works just like the last table, but this is for the second derivative. So what I'm going to do is I'm going to pick a test point in that interval. The next thing I'm going to do is plug that into the second derivative and then come up with a conclusion. And remember, my conclusion is it concave upward or is it concave downward? So let's pick a point between negative infinity and negative 0.528. And I'm thinking, negative 1, right? maybe something in between negative 0.528 and 2.528. My favorite number in there is 0. I always use 0 if I can. And then a number between 2.528 and infinity, 3 looks good to me. Okay, now where am I substituting these values in? I'm substituting into the second derivative. Let me highlight that for you right here. That's where I'm plugging that in. You could also plug it into the factored version, but I tend to go with the real guy. Okay, now what do I care about? Is it positive or negative? Honestly, that's all I care about. So if I substitute in negative 1, okay, I'm going to square it. That's going to give me negative 12 minus 24, which is going to be what? Negative 36 plus 16 is negative. Okay, so once again, negative 1 squared is 1. Negative 12 times 1 is negative 12. Minus 24 because we plugged in a negative 1. So that's going to be negative 36 plus 16 still doesn't take me back to positive. So that's negative. I want to plug in 0 much easier. That 0 plus 16 is a positive value. When I plug in 3, okay, you're going to get 3 squared, which is 9. Negative 12 times 9 is what? Negative 96. And then plus 3 times 4, maybe I should plug this one in. No, it's going to give me a we're talking about, hold on. So I had to stop myself and just plug it in. It's negative 28. By the way, I multiplied negative 12 times 9 all wrong. That's 108. So anyway, negative 20. What matters is I get a negative value there. Okay? So remember, negative means concave downward. I'm just going to put down. Positive means concave upward. I guess I could put the word there. And then negative means that concave downward. Now the question you may have, or later on, will they always alternate like this? Will it always go from downward to upward and back downward? If you're dealing with a polynomial, yes it will. You might want to see the graph of this. Let's take the time and take a look at the graph. Okay, so here's our graph in Desmos. Now listen. All I did was type it in. Remember, I'm typing in the original function, not the derivative, not the second derivative, always the original function, because the questions you're answering are about the original function. You're using the first derivative and the second derivative as tools. So to recap, the first derivative finds increasing, decreasing, relative max, relative min. The second derivative finds concavity for you, and that's all we did for this problem is concavity. But I wanted you to see exactly what this looked like when I typed it in. And notice I can't see where the maximum is. I see a little maximum, a little hump right here, but I can't see how high this goes. So watch. When I zoom out, I'm just hitting the zoom back button, the little negative over to the right, which is actually off the video screen. I have to do this. Then you lose touch of what in the world you're looking at. I mean, finally, it's low enough where I can see it. I can zoom back in just one more time, and that max still shows up. Actually, not for you, it doesn't. Let me back up. There it is. Now, I still can't see what's going on exactly, so what I'm going to do is go into my little wrench over here, which is my graph settings, and I'm going to change the x-axis. So this is not going to be a square graph. But it looks like if I go out to maybe even negative 10, I could see what's going on better. And then I could go over to, let's say, positive 10. I still have a 4 there. I don't care. Okay. Now, much better, right? And so you can see, now we're not square, right? So we're at 200 and we're down here at negative 200 and then we're just at negative 10 to 10 on the x. But we have a relative max right here, and this is concave downward. Remember, our first interval went from negative infinity all the way to, remember they had that decimal, negative 0.528. Now remember, there's negative 2, so negative 0.5 is about here. I'm circling it for you because I can't mark on the graph. Then it changes to concave upward. Now the question is, where does it change? I mean, concave is not the max, right? Because somewhere it flips and starts going back down again. But it is concave upward. And remember, it's actually concave upward to, I'm looking at that decimal, 2.528. So there's 2, there's 3, so 2.5 about here-ish is my x value. And then it turns back to concave downward for the rest of the graph. Now these places, that decimal, which really, remember, was actually the value 1 minus square root of 21 over 3, which is about negative 0.52 something, 8. Those are called inflection points. Inflection points is where the graph changes concavity. It's not at a maximum min, okay? It's somewhere between the max and min it changes. So again, over here at about 2.5 something, so about here it changes concavity again. It goes from concave upward and flips to concave downward. What'd you think about that? Cool, huh? Let's go back to our work. So we talked about, there's our work, you know, it's concave downward showed up on the graph, concave upward showed up on the graph. That was in the middle, and then it went back to concave downward when it had that huge maximum. That was concave downward. Now, these values where it changed are called inflection points. So those critical numbers for the second derivative. As long as it changes concavity, it has to go either from down to up or from up to down. But this guy right here and this guy right here are called inflection points. And that is simply where a graph changes concavity. Now, I didn't actually find the y value associated with that. You can imagine why I don't even want to. But that's what you would have to do to find the real point. All I have right here in front of me are the x values of the inflection points. Alright, so here's the definition of what I was just talking about. The point in which a graph changes concavity is called a point of inflection, or we like to say inflection points. So Theorem 3.8, points of inflection. If you have a point C, f of C, you know, just an xy value, is a point of inflection of the graph of f, then either f double primed of c, what does that mean? It's the second derivative at that point is equal to 0, which is the ones we had a minute ago, or the second derivative does not exist at x equals c, and then over here, think critical number for the second derivative. That's what you should be thinking about. So if I show you a graph of what I mean, so right here we're concave downward, and then somewhere it flips to concave upward, wherever it changes. So about right here would be an inflection point. Now we could redraw the graph of the first and the second derivative there, but you might just trust me that the derivative right here would be 0. Okay, and I should say the second derivative right here would be 0. Okay, now it also could happen where you have the second derivative does not exist. An example of that would be like x to the 1/3 or the cubed root of x. Y'all know what that looks like from pre-cal. That's what that looks like. And there's an inflection point actually right here, and right here this is concave upward. Well, on the other side, you see that's concave downward. But y'all, the first derivative doesn't even exist because it has a vertical tangent line right here, which means the second derivative doesn't exist either. So this works very similar to critical numbers for the first derivative. You're just taking the second derivative, setting it equal to 0, or finding out where it's undefined, like this x to the 1/3 situation. Alright, find the points of inflection for the function. Notice the directions. The first problem we did asked to find concavity for the function. This problem is asking us to find points of inflection, which is really identical to the first directions we did, but we have the extra step of taking the x value and plug it into the original function to find the y value that goes with our inflection points. So here we go. These can be a little bit of work. We need to find the second derivative. To find the second derivative, our first step is required to find the first derivative. So f prime of x equals, so what are we going to do? Well, got a couple of options here. Neither of them are awesome, but you could multiply x minus 2 out 3 times, binomial expansion, and then distribute the x minus 1 inside, and you would have this nice polynomial that's easy to work with, maybe. But you probably want to leave it the way it is and use the product rule and the chain rule in the middle of that process. So product rule, we do the first times the derivative of the second, which is 1. And then plus the second, which is x minus 1, times the derivative of the first. But listen, when we take the derivative of the first, we must use the chain rule. So I pull the 3 in front, rewrite the inside, reduce that power by 1 times the derivative of the inside. So check it again before you start doing a whole lot of work to this thing. You really need to check your work. So I have first derivative of the second plus the second derivative of the first using the chain rule. We're good. So now I'm going to simplify. So I have x minus 2 to the third plus 3, I'm going to move in front there, x minus 1 times x minus 2 squared. You may want to simplify that further. Notice they have a greatest common factor of x minus 2 squared. Now, remember what you've got to do with this. You've got to take another derivative. And then you got to set it equal to 0. So simplifying this as much as possible is the way to go. Alright, so I'm going to factor out an x minus 2 squared. That's going to leave me with an x minus 2 right here because I had 3 of them, so I still have 1 there. And then plus 3 times x minus 1. Keep going. Still working on my first derivative, right? This is x minus 2 squared. And then here, now I'm going to go ahead and write this as x minus 2, distribute the 3, plus 3x minus 3. Why am I distributing the 3? So we can add like terms and be done with this first derivative. So I have x minus 2 squared. And then here I have x plus 3x is 4x, and then negative 2 minus 3 is minus 5. So now I'm ready to take the second derivative. Let's do that in a different color so it's not so overwhelming. So second derivative. Now once again, I need to use the product rule and the chain rule within my problem. So I do first, which is x minus 2 squared, times the derivative of the second. The derivative of 4x minus 5 is just 4. Minus the second plus the second, almost messed that up, 4x minus 5 times the derivative of the first. Now I got to use the chain rule, right? Because I pull the 2 in front. We'll rewrite the inside, reduce that exponent by 1 times the derivative of the inside. Now keep in mind, I've got to do two things with this derivative. I have to find out where it's equal to 0 and where it's undefined. Now, since I have to solve this equation equal to 0, I need to simplify it as much as possible. And the method for simplifying is to factor. Y'all, if you multiply all this out, you're going to get a polynomial that is not easy to factor. So factor now. Notice the common x minus 2, it needs to come out. Okay, just one of them because that's to the first. Now, what does that leave me with? Okay, so I still have an x minus 2 here. I still have a 4 plus, there's a 2 right here, and then there's a 4x minus 5. Now, the idea is I simplify what's in the bracket. So I have x minus 2, and I also have the 4 distributes, so it's 4x minus 8 plus 8x minus 10. So if I rewrite it right out to the side, that's x minus 2 times, now 4x plus 8x is 12x, and then negative 8 minus 10 is minus 18. So that is my second derivative. Now if you want to, and we will do this in a minute anyway, you could factor that common 6 out of there. But remember, what I'm trying to do next is just set the derivative, second derivative, equal to 0. So f double prime of x equal to 0, and we have to find out where that thing is undefined. Now the good news is undefined does not apply because this is a polynomial, and polynomials are defined on the whole real number line, negative infinity to infinity. So really I'm doing this, 0 equals x minus 2. Now I could go ahead and factor out that 6. I'm going to move it in the front, and that's going to leave 2x minus 3. I set each factor separately equal to 0. Now the 6, you don't set it equal to 0. You could even divide both sides by 6 and poof, it's gone. So you have x minus 2 equals 0 and 2x minus 3 equal to 0. I add the 2 and I add the 3 and divide by 2, And these are my two, again, the term is not really critical numbers, but it is. It's critical numbers for the second derivative. So from now, we can make our chart and find out our points of inflection. Now, can I just say these are points of inflection? In a way you can, because we know this is a polynomial. Remember how I told you for a polynomial, it always changes concave downward, concave upward, it alternates. So yes, these are points of inflection. I just need to find the y value. But for every function, even at a point of inflection, you don't know that it changes concavity. You really need to find out for sure, okay? So let's do a table. All right, and our interval is going from negative infinity to the lowest of these two, which is actually 3/2. And then we're going to go from 3/2 to 2, and then we're going to go from 2 to infinity. And remember, what I'm trying to do is take a test point in each of these intervals and plug that test point into the second derivative. All I care about is the second derivative positive or negative? So if we're going from negative infinity to 3/2, 0 is my favorite number in there. If we're going from 3/2 to 2, that's not as much fun. That's like 1.5 to 2, right? Nothing wrong with using a decimal. I'm just going to use 1.75. And then something from 2 to infinity, let's pick 3. Now remember, I'm plugging this into the second derivative. I've got the second derivative highlighted down here for us. That helps. So 0 minus 2, when I plug that in, 0 minus 2 gives me a negative number. And then 12 times 0 minus 18 also gives me a negative. Y'all, a negative times a negative is overall a positive. 1.75 plugged in. 1.75 minus 2 is going to give me a negative number. 12 times 1.75 minus 18. 12 times 1.75 is bigger than 18. Minus 18 is a positive number. If you want to type it in your calculator, feel free. Don't trust that quick analysis. That gives me a negative times a positive is always a negative. Well, plug in 3. 3 minus 2 is a positive number. 12 times 3 is 36 minus 18 is also a positive number. Positive times positive is always a positive. Now, what did we find out? This one, remember, plus means we're concave upward. I'm just going to write the word upward. Remember, I'm talking about concavity, though. A negative means we're concave downward. A plus means we're concave upward again. So that truly does mean our inflection points are 2, got to find the y value, and 3/2, got to find the y value. How am I going to find the y value? I'm going to plug it into my original function, which I got highlighted up here. That's the guy we got to go to. Always to find y values, you're talking original function. When you're talking about testing intervals, it's either the first or second derivative, depending on what you're trying to find. In this section, it's the second derivative. So I'll take the 2 and I plug it in my original function. Now 2 minus 2 is 0. 0 times 1 is 0, so my answer there is 0. Okay, so again, I'm taking 2 minus 2, right up here, right at the top. 0 to the third is 0. Doesn't even matter what that is. Okay, now 3/2 is a little bit more work. I'm going to write it down. So we have 3/2 minus 2 to the third times 3/2 minus 1. So 3/2 minus 2 is a negative 1/2 to the third. How do I know that? Common denominator, right? 3/2 minus 4/2 is negative 1/2 to the third. Then 3/2 minus 1, that's 3/2 minus 2/2 is 1/2. I'm still simplifying. Negative 1/2 to the third. You remember you can just do negative 1 to the third is negative 1. 2 to the third is 8 times 1/2, which is going to give me negative 1 over 16. And that is my final answer. My inflection points are 2, 0, and 3/2 negative 1 over 16. You want to look at the graph. You're supposed to say, yes, please, show me the graph. All right, so here we go. I've got it typed in. So, and since I'm trying to make this as real world as possible, what it would be like if you type something in, that's all I've done. And I look at this graph and I go, what? What in the world is going on? Well, remember, the last time I graphed something for you in this video, we changed our x values from -10 to 10, and from, see, look at the y values. So I can't really see what's going on here. I can't tell. So it is time to zoom in may help, because it doesn't look like we have any points of inflection whatsoever. But the issue is, I think, is our y scale is so big. So instead, I'm going to go in and change our y values. Let's narrow this down to, say, maybe -10, and then to 10, because right now it doesn't look like we did the problem right. That's a little better, you think? Look, it's still, remember, we found that we were concave upward first, and then concave downward, and then concave upward. Does that look like what's going on? You see that? Let's zoom in some more. Let's zoom in crazy close. Okay, now look right here. I agree, that is definitely concave downward until we get to, and I was kind of just tracing it. Look, and it looks like our minimum is right there, but we're concave downward all the way to, remember, what was our first inflection point? It was 3/2 -1/16. So about 1.5 -1/16, right there. Matter of fact, let's plot that point. So 3/2 -1/16. And we'll label it. And let's also plot our second inflection point, which was 2, 0. Alright, now, it still looks so weird to me. I feel like we need to zoom in more, and then we need to narrow our y values. Okay, so again, that's where it's changing. So it's concave upward, and then at 1.5 right there, it changes to concave downward. And then look over here at 2, it goes back to concave upward. But it is so hard to see on the graph. When I zoomed in there, I could see it. That might help you even more. So again, concave upward, and then at 1.5 it goes back to concave downward, and then it flips again. It's so subtle. We could even change our y value view. One more time. I'm probably overkill on this one, but let's change our y values a little bit. Let's look from, say, -1 to 1. And that might, there it goes, that exaggerates it a lot more. So see, we're concave upward, then it changes to downward, and then it flips to concave upward before it hardly did anything. So what you think about that? You can always check yourself, which is awesome. Desmos is the best thing that ever happened to math. Almost. Okay, so we've got another theorem, Theorem 3.9. It's called the second derivative test. And I'm going to go ahead and tell you the second derivative test is optional. I don't mean it's optional as far as the test goes. I mean it's optional as far as math information. You could live without the second derivative test, and after I read it, I think you'll understand why, but I'll also point it out. It says f is a function for which f prime of c is equal to 0. So that's a regular critical number. And I think this is why they don't say critical number for the first derivative or the second derivative. If you just stick to critical number means first derivative, then you don't get confused. But this is for the first derivative. So if the first derivative has a place where the derivative is equal to 0, and also the second derivative at that critical number is greater than 0 for all x and I, then f has a relative minimum. Okay, now let's think about what that means. Okay, this is saying the second derivative is greater than 0. Remember what that meant? That meant the graph is concave upward. So this is a previous theorem. The second derivative in this section, the second derivative greater than 0 means the graph is concave upward. Well, if a graph is concave upward, then clearly it does have a relative minimum. Okay, if it looks like that. Now, not all concave upward has a relative minimum. So it also has to have a critical number in that interval, if that makes sense. Now look at the second one. The second one says if the second derivative is less than 0. Now, by a previous theorem, the second derivative less than 0 meant you're dealing with concave downward. And if also in that concave downward you have a critical number, or the derivative is equal to 0, then that would be a relative maximum. Now, why don't you need this theorem? Because we already know how to find relative minimums and relative maximums. What we did in the last section is we said if a graph goes from, on the left, decreasing to increasing, then it's going to have a relative minimum as long as you're dealing with a continuous function. If a graph, on the other hand, goes from increasing to decreasing, you're going to have a relative maximum. So we have ways of finding relative maximum and relative minimum already, but this is very convenient, terribly convenient, and so that's why it's worth mentioning and worth doing problems that include the second derivative test. Notice the third line here. It says if the second derivative of c is equal to 0, then the test fails. That doesn't mean you don't have a relative maximum and relative minimum. That means you need to use the first derivative test, the test we talked about just a second ago. Goes from decreasing to increasing or increasing to decreasing. That's the first derivative test. And so if the second derivative is equal to 0 at that point, that just doesn't tell you anything. Okay? Doesn't mean you don't have either one, you just don't know. So let's do a problem where we use the second derivative test. It says use the second derivative test for the function f of x equals 2 sine of x plus cosine of 2x. Recognize that, it's a double angle, right? On 0 to 2 pi. Notice this time, like I was supposed to, I gave you an interval for the trig function because we can't look over the whole real number line. Most of these trig functions oscillate forever, and so you would have maximum and minimums all day long. So we're supposed to use the second derivative test. Remember, we just learned that. So to use the second derivative test, what do we have to do? Well, we have to find the second derivative, am I right? So first we have to find the first derivative, and we have to find critical numbers. So first let's write what we do. We're going to take the first derivative. So these are steps over here. Find critical numbers. I'm going to put C in for critical numbers. Okay. Take second derivative. And then substitute critical numbers. That's all we got to do. Okay, so take the first derivative. So the derivative of 2 sine of x we know is 2 cosine of x. Again, I'm using the scalar multiple property, so the 2 comes down, and the derivative of sine of x is cosine of x. Now, to evaluate the derivative of cosine of 2x, I've got to use the chain rule. So first, the derivative of the outside. The derivative of cosine is negative sine. You rewrite the inside, but don't forget times the derivative of the inside. Everybody feels a little bit better if that's rewritten, so at least I do. F prime of x is 2 cosine of x minus this 2 I'm going to write in front of the sine of 2x like a coefficient. That's what we have. Now remember, what we got to do is we have to solve this equation because we got to find critical numbers. So I have to find out where is this derivative equal to 0 and where is this derivative undefined. Now the good news is, as far as undefined goes, we don't have to worry about that. Cosine of x and sine of x, no matter if the 2 is in there or not, are defined everywhere because we have no zeros in the denominator. The trig function sine and cosine are defined on the whole real number line. So there's no issue here, but we still have to solve this equation. So I have 0 equals 2 cosine of x minus 2 sine of 2x. Now, you may remember from your trig class that to solve an equation, a trig equation, we really need these insides to match. So we have a double angle for sine of 2x. I know you might not know it right off the top of your head. It's 2 sine of x cosine of x. So I'm going to replace sine of 2x with the double angle formula, which is 2 sine of x cosine of x. So now I have 2 cosine of x minus this 2 is already there times 2 sine of x cosine of x. Now again, why did I do that? Because I don't want to solve this equation with this cosine function only having an x as the argument and this having a 2x as the argument. That's going to make it extremely difficult to solve. So now, let's simplify this. This is going to be minus 4 sine of x times cosine of x. Now I'm still stuck. How am I going to solve this? Well, notice that where's the greatest common factor? There's a 2 common to both of these terms, and there's a cosine of x common to both of these terms. So I'm going to pull that out. 2 cosine of x, and then I'm left with 1 minus 2 sine of x. And then I set each one of these separately equal to 0. So I have 2 cosine of x equal to 0, and I have 1 minus 2 sine of x equal to 0. Because once it's factored, you set each factor equal to 0. So I divide both sides by 2 here. So I get cosine of x is equal to 0. And I ask myself, where between 0 and 2 pi now is cosine of x equal to 0? And it happens at 2 different places. Remember, on the unit circle, cosine is an x value. X is 0 up here and down here. So I get x is equal to pi over 2. And I'll get also x is 3 pi over 2. Now, those are critical numbers, okay, for the first derivative. Here, I'm going to add the 2 sine of x over, and then I'm going to rewrite it with my sides switched. Do you agree that's the same thing? Okay, you can subtract the 1, divide by negative 1. Divide by 2, and then ask yourself where on the unit circle between 0 and 2 pi is sine of x equal to 1/2. Now remember, sine is a y value, and that's going to be here and here, which happens to be x is equal to pi over 6, and x is equal to 5 pi over 6. Okay, now these guys are critical numbers. Now what am I supposed to do with those critical numbers? I'm supposed to substitute them into the second derivative. Uh-oh, so I got to find the second derivative too? Yep, sure do. All right, so here we go. Second derivative, f double primed of x. So our first derivative was back up here, okay, in red. Now the second derivative, the derivative of 2 cosine of x is going to be negative 2 sine of x, right? Because the derivative of cosine is negative sine, I went ahead and multiplied by that 2. The derivative of negative 2 sine of 2x, I got to use the chain rule, okay? So first of all, the derivative of sine is cosine, so it would be minus 2 cosine, rewrite the inside, times 2. So simplify, this is negative 2 sine of x minus 4 cosine of 2x. All right, so that is our second derivative. We'll square that off. Now what are we supposed to do with the second derivative? We're supposed to plug in the critical numbers. Okay, now I can do one of two things. I can just add a new page to this. Let's do that so we can go back and look at it. Now what I've done is I've erased, and I've left our directions over here. So remember, we found the first derivative, we found the critical numbers, we took the second derivative, that's at the bottom of the page in red, and we have our 4 critical numbers. So what I'm supposed to do is substitute these 4 critical numbers individually into our second derivative, okay? And then we're supposed to come up with a conclusion for that, and we might have to go back and revisit to see what we found, right? So f double primed of, let's do pi over 2 first. Okay, so I'm doing negative 2 sine of pi over 2 minus 4 cosine of 2 times pi over 2. When I simplify that, now we know the sine of pi over 2 is 1, so that's negative 2 times 1 minus 4. The cosine, these twos cancel. Cosine of pi is negative 1, so I have negative 6. Okay, now what matters is that's less than 0. You remember when the second derivative is less than 0, you're talking about concave downward. So would that not give us a max right there? Because concave downward means you have a relative max. Okay, let's find the second derivative with 3 pi over 2 plugged in. I'm not doing these in any particular order, by the way. So that's negative 2 sine of 3 pi over 2 minus 4 cosine of 2 times 3 pi over 2. Now, sine of 3 pi over 2, remember that's at the bottom, sine's a y value, so that's negative 2 times negative 1, minus 4. Now, these twos cancel. The cosine of 3 pi is the same as the cosine of pi. That's negative 1. So I've got negative 2 times negative 1, which is 2 plus 4 gives me 6. 6 is greater than 0, which means we were dealing with a concave upward situation. So that's going to give us a min value. So we have a relative minimum right there. And then I'm going to find f double primed of pi over 6, which is actually the lowest value on our angle list. So that comes before these two if you're thinking left or right. But negative 2 sine of pi over 6 minus 4 cosine of 2 times pi over 6. Now, the sine of pi over 6, negative 2 comes down. The sine of pi over 6 is the y value. Remember where pi over 6 is? The y value right there is 1/2. Your calculator will tell you this as well. These twos cancel, so I'm really calculating the cosine of pi over 3, which is actually 1/2 also. And you've got negative 2 times 1/2 is negative 1 minus 2, which is negative 3. Now what matters is that's less than 0. When your second derivative is less than 0, you're talking about a concave downward situation, which gives us a max at pi over 6. And then the last one, f double primed of 5 pi over 6, is negative 2 sine of 5 pi over 6 minus 4 times the cosine of 2 times 5 pi over 6. Now, the sine of 5 pi over 6, you remember where 5 pi over 6 is? It is in the second quadrant, close to pi. Sine is positive there, and it's going to be a positive 1/2. So it's negative 2 times 1/2 minus 4. Now, this 2 cancels there, so I'm really calculating the cosine of 5 pi over 3. So where is 5 pi over 3? That's 1, 2, 3, 4. 5 pi over 3 is right down here. The cosine there is positive, and it's the short one, so it's positive 1/2. So I've got negative 1 minus 2, which is negative 3, which is less than 0. Did I do that right? I think so. So negative 3 is how to think about it, because it's the same calculation as our pi over 6, wasn't it? Anyway, so negative 3 is less than 0. That means I'm concave downward, which is going to give me a max. I feel like something is wrong with that because these alternated. Okay, folks, so I had to pause it for a minute to find my error. I bet you found it. You're probably sitting there going, but Miss Wilson, but Miss Wilson. I know you found it. Look, it's right back here. You found it a long time ago and you had to just let it go. But thank goodness I found it, and I'm not going to redo this video. We're just going to go with that. Look, negative 2 minus 4 times negative 1 is negative 2 plus 4, which is definitely not negative 6. It is a positive 2. And that also means that I am going to erase this part. Sorry about the error, y'all. That's greater than 0. And when your second derivative is greater than 0, not less than 0, you are concave upward, which means we have a minimum at pi over 2. So I go back, and when I said we had a max at pi over 2, we sure don't. We have a minimum at pi over 2. Now that makes more sense to me because I was looking for the pattern there, and things were not looking good. Not looking good there at all. Now, what I don't have space for, and you probably don't have time for in your life, is to find the y values. Now, I had already done that. And remember, how do you find a y value? You take your x value and you plug that into the original function. I know every one of you are capable of doing that. And I have a list right in front of me with them already done for you. So in order, the lowest x value on this list was actually pi over 6. And the y value I got for that in decimal form is 1.5 or 3/2. And then the next one in order is pi over 2. And remember, that was the minimum, so pi over 6, 1/2 was a max, a relative max. Pi over 2, 1 is a min, a relative min. And then 5 pi over 6, 1.5 was a max. And then the last point was 3 pi over 2. I'm going to write it way down here, y'all. 3 pi over 2. And that y value was -3. And that was a minimum. So there's my results, squared off in green over there with a page full of calculations. Remember, that's just half the problem. Woof, there's the other half of the problem. It's a ton of work, isn't it? Hopefully yours is neater than mine. It's tough writing on these squirrely screens sometimes. But I know you want to see the graph, right? I know you're begging to see the graph. So let's take a look at the graph. Okay, folks, here we go. So look, if you look to the left, look at all that I've got typed in. I've got y equals 2 sine of x plus cosine of 2x. Be sure to use parentheses around your argument and your trig function. That way Desmos knows exactly what you're taking the sine and the cosine of. And then I labeled all of our maximum, and relative minimum values. And look, the good news is they landed on the graph. So you don't want your point to be off the graph yet. That you say that's your maximum, it has to be on the graph. And so we said that pi over 6, 1.5 was a max, and look at it up there. It is definitely a max. And we said that pi over 2, 1 was a minimum, and it is a minimum. And we also said 5 pi over 6, 1.5 was a max. But look, 3 pi over 2, -3 fell off my graph. But it was down there at -3. So let me scoot out just a little bit. You want to make sure you see everything you're looking for. And there he is, down there. Now notice, this is symmetric. Looks like a molar, right, a tooth. But this is very symmetric. This goes on forever, and that's why I had to give you that interval of 0 to 2 pi to take a look at. If I zoom way out, just so you can see what it looks like. Very cool, right? Looks like teeth. Just a whole bunch of teeth lined up. That's a cool graph. Okay, let's do one more problem and call this video done. So I got a problem here for you right out of the homework. Hence the image is blurry because I had to make it much bigger, and so the resolution is not good. I apologize. It's not your vision. It's just, it was a much smaller image than that when I copied it. So here we are. They want us to graph f of x, which is already done, by the way, f prime of x and f double prime of x on the same axis. Now we could do that, so I could graph it right on top of this one, but I decided to go ahead and scale off 2 more xy axis to do f prime of x and f double prime of x separately. If you feel like that's what you need to do in your homework as well, feel free. So I'm scaling off everything just like it. So they have that as 2 and that is 4, and this is -2 and -4. I'm going to do the same thing over here. Let's get that over with. 1, 2, -1, -2, 2, 4, and -2, -4. There we go. All right. Now, in red, let's see if we can't graph our first derivative. Now, all we're doing is looking at the function. We don't know what this function is. We're just looking at the function and trying to graph our first derivative. Now, here are things that I notice. When I graph a first derivative, right? First derivative means the slope of the tangent line. So over here, the slope of the tangent line, because this is increasing, is all positive. So I need to have positive values on my graph. Over here, it's all negative. So I need to have negative values on my graph. Here, it's all positive. Now, the first thing to do and the easiest thing to do is find out where the derivative is 0 and make those marks first. So right here, I see the derivative is 0. I don't think they mean that to be on the y-axis. It doesn't look like it is to me. And in between 1 and 2, the derivative is 0. So when I copy that onto my derivative graph, then I've got to have a 0 right here to represent that x value, right? And a 0 between 1 and 2 to represent that x value. Now remember, everything in between, right here, between those two derivative equals to 0, is a negative slope. Okay, so that means the slope is negative in between here, so I need to make it negative. Now what the value of it is, I'm not going to get all hung up in that. I just know it's negative, okay, and those have to connect up. Now over here, to the right of that 3/2 value, the slope is positive, so that means it's above the x-axis. And over here, the slope is positive as well, because it's an increasing graph everywhere along here. You have a tangent line, and it gets closer and closer to 0, so the further it gets away, the steeper it is. So your first derivative looks similar to that. Not exact, but similar, and that's all I'm going for. Okay, now, here we go again. I'm supposed to graph the second derivative from this. But honest to goodness, you don't really want to do that. What you really want to do is graph your second derivative from here, okay? Because all it is the derivative of the first derivative. So somewhere along here, this derivative is equal to 0. Where? About here. It could be 1. On my graph, it looks like it's almost 1. And I'm just going to say it's almost 1 there. Now, on the right side, that's an increasing graph, right? The slope gets steeper and steeper and steeper, so it gets higher and higher, but it's increasing, which means the derivative of increasing is a positive number. So over to the right, it's got to be positive. But on the left side, my slopes all along here are decreasing, right? So everything to the left of that 0 point, which is right there, is a negative slope. So it's got to be negative over here. And there we go. Now again, this is just rough. This is not exact that I'm doing here, okay? But rough, and that's it. So original function, first derivative, second derivative. Pretty cool, huh? Okay, well that wraps up this video. Join me when you're ready after you do some of these homework problems for the next section, which is infinite limits. Okay? Hey, by the way, I said that wrong. We've already done infinite limits. We did that in the last sections. It's limits and infinity, and I always get those names confused. And when I do the video, I'll explain the difference between the two, and never in my head is the name of that straight. Hope you have a wonderful day. See you soon.